All right, welcome back again, everybody. Today we're doing section 14.5, and this one's all about the chain rule, or maybe I should call it the chain rules, as you'll see. Um, this one's not too bad, might sound a little bit worse than it is, but let's get started. All right, the chain rule, the most important differentiation rule. Okay, so the overview is this. We're going to talk about the chain rule. We'll define it. We are actually going to prove the chain rule. And to do the proof of the chain rule, we need that characterization of differentiability that we developed in the previous section. So we'll need that. Then we're going to talk about diagrams, basically dependence diagrams. That is going to help us compute the chain rules for these various functions. Then we'll finish up with implicit differentiation and the implicit function theorem, which actually gives us kind of a shortcut for computing derivatives of functions that are defined implicitly. Okay, so here we go. One of the more important differentiation rules, or maybe the most important, in Calc 1 is the chain rule. So I do hope your instructor emphasized it quite a lot. Basically, it provides a formula for differentiating a composition of functions, which we want to do all the time. Because a lot of times we want to take functions and nest them with other functions and keep doing this. And we want to know how much they change, right? What's the change of that composition? So the question for us is, how can we extend this to a function of two or more variables, right? So just ponder that for a moment. How do we extend the chain rule to a function of two or more variables? Because if I've got functions of multiple variables, like where do I do the composition? Like if I've got, f of x, y, and then I have another function that I want to plug into that one, do I plug it in for x? Do I plug it in for y? How do I compute the derivative? All that stuff, right? So it's an interesting question. With multivariable function, it actually turns out that there are many different chain rules, and they're entirely dependent on the structure of the composition. So the idea here is that if you want to know the chain rule for some multivariable function, or like you're composing a bunch of functions, it depends on the function. That's really what it is. There's no like single way to do it. I mean, I should say there's no single formula. The formula depends on the chain itself. So one other thing I want to say is this: the textbook only covers a specific class of compositions or dependence relationships, but we're going to explore it in more generality, just general chain rules. Some of you will see this in the future as well. The idea is that your compositions don't all have to be trees. The book only talks about compositions that take the structure of a tree diagram, but the compositions don't have to be trees. They can be all sorts of crazy things. Some of you will actually study something called graph theory, and this is where you would need something like that. Anytime you want to talk about a more interconnected web of vertices and edges and nodes, and you wanted to talk about differentials going between all these things, you would need this more general chain rule theory. Okay, so let's go back to Calculus 1 again for a minute. I know I say that a lot in this class. Let's go back to Calc 1 for a minute. The chain rule for a single variable function basically had this form. If f and g are differentiable functions, then so is their composition. And the way that you compute the derivative is you do the derivative of the outside function with the inside function left alone times the derivative of the inside function, g prime of f times g prime with f left alone times f prime of x. In Leibniz notation, you can write it like this, and this is going to be one of those situations where Leibniz notation is superior, especially because now we've got so many different variables, and we're going to have multiple chain rules for each function to compute these partial derivatives. Leibniz notation is going to be the superior choice in this case. So how did you do it back in Calc 1? Well, dy dx was dy du times du dx, and that result is just really elegant. It's basically saying that you do the derivative of y with respect to u is the function that you're plugging in, right? And then you multiply by the derivative of u with respect to x. And that's it. That's how you compute the derivative of a composition. All right, so let's look at the first case. So in a function of two variables, this is what it looks like. Suppose that z equals f of x, y is a differentiable function of x and y, where x is a function of t and y is a function of t. and those are both differentiable functions of t, then what we know is that z is also a differentiable function of t, and the chain rule becomes this. That's it right there. So dz dt is partial z partial x times dx dt, partial z partial y times dy dt. Okay? Now, this is one that I want you to kind of stare at for a minute and just look at it, read over it for a minute, look at those pieces, and then we'll talk about it in just a moment. Okay, a couple things I want to point out about this chain rule. For one, notice that this is a partial derivative because z is a function of two variables, x and y. So dz dx doesn't make sense because z is a function of more than one variable. So all you can really talk about is a partial. So partial z, partial x. Then it's almost like we're going to use the chain rule that we know and love from Calc 1 again, right? It's going to be partial z, partial x times dx dt. Now, x is a function of a single variable. So it makes sense to use dx dt. It's a function of a single variable. There's only one derivative you could be talking about, the one with respect to t. Now, this gives us the, I'll say the chain with respect to x. This is going to give us the chain with respect to y, and then we're going to add up those results. So that's kind of the structure, right? The theme of this idea. dz dt is this plus this, right? So you compute the partials and do that. All right, now what we're going to do, since I'm assuming most of you did not see a proof of the chain rule in Calc 1, we are going to prove this case right here, right now in Calc 3 using the characterization of differentiability that we developed in the previous section. So here we go. All right, try to follow here. A change of delta t produces changes of delta x in x and delta y in y, because those are both functions of t. Now, these changes in x and y in turn produce a change of delta z in z. So by the characterization of a differentiable function, we can write the increment of z in this form. That's what we established back in the previous section. Partial f, partial x, or maybe I should say partial z, my bad, partial z, partial x, delta x, partial z, partial y, delta y. And then you had these two epsilon functions. These epsilon functions are just the corresponding differences in the slopes of the secant lines and the tangent lines. And they both go to 0 as the increments go to 0. That was the idea. So a function is differentiable if you can write it in this way, where these two functions go to 0 as delta x and delta y go to 0. Now, take this equation here and divide both sides by delta t. So divided by delta t, divided by delta t, distribute the delta t through the different terms, and it becomes this. Right. Yeah, now we're going to see why we needed that characterization in the previous section. Here we go. So here is that equation one more time. Now, what we want to do is we want to take the limit as delta t goes to 0. So as delta t goes to 0, that means delta x goes to 0 because g is differentiable. And if g is a differentiable function at a point, that means it's continuous at that point. Differentiability implies continuity. So as delta t goes to 0, delta x goes to 0. Check. Similarly, delta y is going to go to 0. Check. And then consequently, that means that epsilon 1 and epsilon 2 are going to go to 0. That's what we needed, right? So here is the calculation. What is dz dt? Well, by definition, it's the limit as delta t goes to 0 of the difference quotient. And we have a formula for it right up here. So I'm going to replace this with this. And then I'm going to distribute the limit using the limit laws, right? So I want to walk through this particular line in detail. So once I take this limit and I distribute it to this, here's what I get. This limit only depends on t. So it's going to treat this like a constant. I can pull it out of the limit. Sorry, pull it out of the limit. And then we've got this limit right here. Same thing. This limit only applies to delta t. So it's going to treat this as a constant, and I can move that constant out of the limit. This is inside the limit. Now I could do limit of a product as a product of the limits. Why? Because both of these limits actually exist. Remember, you can't use those properties of limits unless you know both of the limits actually exist. But this limit does exist. It's 0. This limit does exist. Why? Because we said that x was a differentiable function of t. So that means that if I take the limit of the difference quotient as the denominator goes to 0, it exists. Same thing here. This limit exists. This limit exists. So the distribution of that limit operator to all of those terms and all of those factors and pulling out the constants, all of that is fully justified. Now, what is this? This is quite literally dx dt. This is dy dt. This goes to 0. This is dx dt. This goes to 0. This is dy dt. And then lo and behold, we're left with gone, gone, just the beginning here, which is exactly what we wanted to prove. And that's the proof. That's the proof of the chain rule. So this is one of the reasons why that characterization of differentiability is important, because it makes proofs like this much more straightforward. Try to do the proof of the chain rule without it. You might see that it's actually not that easy to do. Okay. All right. So here we go. This is one I want you to try. So you remember the formula. You're just going to like basically multiply those things and then add the results. And we're going to get some shortcuts when we get to the diagrams section here. So if z is given by this function, x is given by this function, y is given by this function, I want you to try to find dz dt. So think about how you would start first. Okay. Say something out loud to yourself, something to give yourself that verbal feedback. And now try to work it out. What is dz dt? The change in z with respect to t. Right, here we go. Oops, there we go. All right, using the chain rule, we know that this is the formula here. Partial z partial x times dx dt plus partial z partial y times dy dt. We can compute all of these partials and all of these single derivatives just using the good old differentiation rules, and we get this. This is partial z partial x dx dt, partial z partial y, dy dt. Multiply together, combine like terms a little bit, and then you get this mess right here. So that is the change in z with respect to t. So yeah, what does this mean? This basically is telling you the rate of change of z with respect to t as the point x comma y moves along the curve c given by these values right here. So that's really handy. So as the point x comma y moves along this curve, which is basically an ellipse, right? This is going to give you the change in z as your point moves along that ellipse in the xy plane. That's the idea. Oh, I'm sorry, not an ellipse. I moved this over here. It's a circle. Sorry, it's a circle. Okay. All right. So now let's say we have wait, where did I leave off here? Oh yeah. So now let's increase the number of branches in the tree, you could say. So suppose that z is still a differentiable function of x and y. But now both x and y are also going to be differentiable functions of s and t. All right, so it's kind of like this double tree, right? So one thing is z can no longer be written as a single function, I'm sorry, as a function of a single variable, right? It's not like z of t like it was before. It's still going to be z of s and t. So we can only talk about partials. Partial with respect to s, partial with respect to t. And what does the formula look like? Pretty much the same thing you would expect. Partial z partial x, partial x partial s, plus partial z partial y partial s. And then do the same thing for t. That's why we're getting two formulas. We're getting two formulas here. Here, the variables s and t are the independent variables. Those are the ones that are, independent, right? X and y are what we call intermediate variables. So they're variables that are kind of in the middle of the tree. as we're going to see in just a minute here. And this part I already said. So under this composition, z is a function of two variables. That's why we're getting partial derivatives instead of just a single derivative like we did with case one. All right, now I said that really fast, but I don't know if you're like me, but when I see this and I see this, I start to get very overwhelmed with how much stuff I guess I'm supposed to memorize or remember. And I'm like, how am I going to remember all these formulas? And this is going into that and yada, yada, yada. It's hard, but that's why we have diagrams. So diagrams basically allow you to visually organize the dependence relationships that we're talking about here. And the diagrams are going to make remembering the chain rules super easy. That's what's fun about this. So yeah, there you go. As you might imagine, like compositions of multivariable functions can get complex very quickly, and deducing the associated chain rules can be difficult to keep track of. I mean, this is just like 2 steps, right? Like what if we had 4, 5, 6, 7, n many steps? What's the chain rule for that? So it's handy to use what we call a diagram to determine and remember the chain rules for multivariable functions, as you're going to see in a minute. So what is a diagram? A diagram is just a graph with vertices and directed edges that let us visualize the compositions or the dependence relationships. And then a directed path through the diagram represents a composition. Let's look at this one here. So in theorem 3, was it 3? Or was it 2? No, it was 3. Yeah, so in theorem 3, we can use this tree diagram. So let me zoom in for a minute. All right, so z was a function of x and y. So that means if you had something for x, you can get a value for z. If you had something for y, I'm sorry, if you had values for x and y, you could get a value of z. So they're like pointing up to z. But also, each one of these functions, x and y, were functions of s and t. So these arrows are giving you the dependence relationships, right? That's basically it. And then what we're going to do is for the chain rules, each one of these edges, each one of these arrows is going to correspond to a derivative, either a partial derivative or just a straight up derivative. And then what we do is we multiply the derivatives along the paths from independent variable to the dependent variable. And then we add up the products to produce the associated chain rule. So let's look at the diagram again. If I wanted to know the partial derivative of z with respect to s, there's 2 paths I have to take. This one and this one. So what am I going to get? I'm going to get a product of this and this, partial z, partial x, I'm sorry, partial z, partial x, partial s, plus this other path right here, partial z, partial y, partial s. And then I add those results. And that's how we do that. There we go. That's how we get this one right here. So it's literally, you make the tree diagram, or I shouldn't say that, you make the diagram, and then you look at the dependency relationships, and then you just multiply partials along those paths, and then add all of the different paths up. So this one plus this one gives you the partial of z with respect to s. Do the same thing for t. So t, it's this way and this way, so it'll be partial z, partial x times partial x, partial t, plus, where was it here? Partial z, partial y, partial t. And there it is. That's it. That's the chain rule. That's the chain rule. So these diagrams are super helpful. They're super helpful. They're what you're going to use to remember all of these things, okay? Yes, all right. So here's one where, let's see, I want you to try this one on your own first. Oh, I didn't do the, wait, I didn't really? I could have sworn I did. I thought I had the diagram. Well, okay, do this one on your own. We'll do the diagram together too. So think about how you would start. Okay, now say something. What do you want to do to get started? Right, and now try to compute it on your own. Big hint, make a diagram. Okay, let's do this one together now. Okay, so here I see that z is a function of x and y. So my diagram would start like this, x and y. Okay, and then x is a function of s and t, y is a function of s and t. So we have a tree diagram like before. So s t, s t. So what is our chain rule, or what are our chain rules going to look like? It's going to look like this, or they're going to look like this. Partial z, partial s is going to be, let's see, this path and this path. So it'll be a partial z, partial x, partial x, partial s, plus partial z, partial y, partial s, and then do the same thing for t. So we'll get partial z, partial x, partial t, partial z, partial y, partial t. There we go. Those are the chain rules right there. Now we just compute all these partials and then plug them in, and we get this. There we go. So I won't go through all the nitty gritty. I'm sure you can kind of do this part on your own. Partial z, partial x is this. Partial x, partial t. I'm sorry, partial x, partial s is this, and so on and so on. I won't dwell. You're welcome to verify that these are correct. Hopefully I don't have any typos, but that's the idea. Right. Now, here is the catch. So I mentioned this earlier, but the composition structure does not need to be a tree. And this is something that the book does not mention. So your function, your dependence relationships may not just be simple trees, right? Where you kind of just go this way. You can have loops, you can have cycles, you can have all sorts of different things. So this is one where um, here's what I want you to do. We're going to do this together. We're going to derive the chain rules for this function here, where z is a function of x and y is a function of x and t. So all I want you to do before you try to compute it is create the diagram. So I'm just going to do this right away. Given these dependencies, make a diagram that illustrates these dependencies. Okay, now let's take a look at it together. Hopefully yours may not look the same, but it should be equivalent. It should be equivalent. Here we go. This is the diagram. Let me zoom in on this, and I'll explain some things in just a minute. So z is a function of x and y. So that means here's z, x goes to z, y goes to z. All right? Now, y is a function of both x and t. So x also goes to y, and t goes to y, right? So because z is a function of x and y, we're going to have two partials. We're going to have a partial with respect to x, and we're going to have a partial with respect to t as well. Yeah, because it's going like this. I'm sorry. This, there's this, there's this, there's all of these paths, right? So rather than get all bogged down with everything, just follow the paths. Here we go. So let's do the easy one first. Let's do this one. There we go. So if I want to know the partial of z with respect to t, there's only one path. It's this path right here. So I do partial z partial y times partial y partial t. Boom. Okay, now here's where things get a little interesting. To get the partial of z with respect to x, there's two paths that I have to add up. There's this one, and then there's this direct one. So same idea. I'm going to do this one right here. I'm just calling it f sub 1, which is the partial with respect to x before any substitution occurs. That's why I wanted to use a different letter. I didn't want to write partial z partial x because that's like what we want. This is the partial with respect to x before any substitution is performed. Okay, and then here is the other path. So we get this first path plus partial z partial y partial x. And that's it. That's how you would produce the chain rule for something where there's like a loop. All right. So just remember that the dependencies do not need to be trees. They can be like anything. And that's really what this looks like here. Now, this might be a little confusing, but here's what I want you to try on your own. let z be x squared plus y squared, and let y be x cubed plus t squared. So here's what I want you to do. I won't pause and do it myself, but if you want to do it on your own, you can. I want you to use the chain rule for, which one is it? That one, yeah. Is that right? For dz dt, hold on, I meant to see x or t? I'm sorry, I meant to say x. Or is it t? Now I can't remember. Shoot, I can't remember if this is a typo. I'll just say this. Use the chain rules that are listed here to compute the partials with respect to x and t for these functions, okay? Then what I want you to try is actually do the substitutions. So take y and plug it into z. So basically take this and plug it in here, and then do the partials again. And then you'll see that you actually get the same result. So the beauty of this is you don't need to perform the composition to actually compute the derivative of the chain, right? So try to do it both ways. Sorry if there's a typo here, but try to use the formulas we just came up with and then perform the composition and just do the derivatives straight up, the partial derivatives. And they should be the same. Okay. All right, so in general, this one actually is in the book too. So I think it is. Yeah, I'm pretty sure it is actually in the book. If you just have a general tree structure where your compositions are just trees, then this is the generalized chain rule for each partial derivative of f. So if f is a differentiable function of n variables and each x sub I is a differentiable function of m variables, then f can be written as a function of these m variables. And for each one of these m variables, the partial derivative of f with respect to t sub I is multiplying along the path and adding up the results. More concisely, it's written like this. Excuse me, written like this. So here is a situation where the notation can look very overwhelming and very confusing. So this is one of those times where you should just take a deep breath and go through it piece by piece. So let me try to make sense of what I'm even looking at, right? So this here is the partial derivative of f with respect to t sub I. Yes, t sub I. So in this case, t sub I is something that is, we're going to say not changing for just a moment here. The partial of f with respect to t sub I. And the way that we compute that is we do partial of f with respect to x1 times partial of x1 with respect to ti. Then we add partial f partial x2, partial x2 partial ti. And then we keep going. So notice that the ti here is not changing because we're getting the partial of f with respect to that ti. What is changing is the intermediate variables. The intermediate variables. The independent variable is not changing. The intermediate variable is changing. So written concisely, that's what this is saying. The intermediate variables are changing. They're going from 1 to n because there are n of those intermediate variables. And for each one of those independent variables, you get a partial derivative. Boom. So this is a partial derivative with respect to one of the independent variables. And this is what the formula is. Okay, we're going to do it for 3. So here's one that I want you to try on your own. If u is given by this function here of 3 variables, and x is given by this function here of 3 variables, and y is this function here of 3 variables, and z is this function here of 3 variables, I want you to just find one partial derivative, the partial of u with respect to s at these values. Okay, so think about this one for a minute. Okay, now, what's a good place to start? Say something out loud to give yourself a boost for how to start. Right, now try to write it down. So try to do the calculations and we'll do it together in a minute. If you want a good hint, make a tree diagram first. All right, here we go. So with this thing, first thing I would do is make a diagram. I need to see the dependence relationships between all of these variables. So this one happens to look like this. It is a tree diagram. Uh, Again, u is a function of three variables, right? X, Y, Z. But each one of those variables, each one of those intermediate variables is a function of three other variables, R, S, and T. So R, S, T, R, S, T, R, S, T. That's why the diagram is handy. So writing down the diagram for the dependence relationship, that's the way to go. Now, if you need to compute what? Partial u with respect to s, we just need to multiply all those paths. I should say, multiply along those paths and then add up all the paths. So let's see, we're doing s. Let me get a highlighter. So we need that, we need that, and we need that. And we're going to add up those three things. So we'll do partial u, partial x, partial s, partial y, partial x, partial y, partial s, partial, oh, is that a typo? That is a typo. Sorry, this should be a u. There we go. And this should be a u too. That's a copy paste error, my bad. X, 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 Y, 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 Z, Z, Z. Copy paste error, my apologies. Yes, so we'll need this one, and then we add up all the results, okay? So here we go, just like so. And then compute all those partials. Partial u, partial x, differentiate that with respect to x. Partial x, partial s, differentiate that with respect to s. Multiply the results, and you get this. There you go. Continue. So do the others, right? I won't go through I won't say all of them out loud, but you go through the rest, and you end up getting this complete partial of u with respect to s. Okay, now here's the thing. We have actually been asked to evaluate this partial derivative at this point, when r is 2, s is 1, and t is 0. So the good news is this. Instead of substituting back in all of the functions for x and y, literally like instead of taking this and plugging it in for x and this and plugging it in for y, don't do all that. Just evaluate these individual functions at the point and then use those numbers as a result. So don't do all the compositions. That's the thing. You don't have to do all the compositions. You can just do the individual evaluations and then multiply. So that's what I'm doing right here. So if I evaluate x at this point, I get 2. If I evaluate y at this point, I get 2. If I evaluate z at this point, I get 0. So now everywhere that I see an x, y, or a z in this formula, I can just put those numbers. So what is this thing evaluated at 2, 1, 0? It's this, 192. Right. Okay, so now that we have the chain rule, we can actually help us do implicit differentiation even easier, as you're going to see. This is kind of cool. So we've got a generalized version of the chain rule. We know how to compute all these different chain rules, so we can get a more complete description of implicit differentiation. So suppose we have an equation of this form, f of x comma y equals 0. And what we know, or what we're going to say we know, is that y is implicitly a differentiable function of x. So what we're saying is that we could, if we wanted to, write y as f of x. Okay, so really what we're saying is that this could be written like that. We just don't want to have to do that because that can be really, really messy. So when we use the chain rule on this, we get that partial f partial x dx dx, partial f partial y dy dx, basically just differentiate this thing on both sides implicitly, we get this. But dx dx is equal to 1, and as long as this thing is not equal to 0, we can write this. dy dx is equal to f sub x over f sub y, and we take the negative. Okay, let me go back real quick. Let me go back to this equation here. dy dx is what we want. That's the slope of the tangent line, right? This is what we want. We can solve for that as long as this thing is not zero. So as long as the partial of f with respect to y is not zero, we get this, which is really handy, as you're going to see in a minute. Yeah, here we go. A couple caveats here. So f has to be defined on a disk containing AB, where f of AB is equal to 0. That partial can't be equal to 0 because then we can't divide. We do need these things to be continuous on the disk. Then this equation defines y as a function of x near the point AB, and the function is differentiable, and this is the formula for it. It's like partial with respect to x over partial with respect to y, opposite. Okay, so here's a fun one. All right, so this is one that I do in Calc 1. So this is the equation that gives you the folium of Descartes. It's the one that looks a little bit like this. Oh geez, it's like something like that. I know I butchered that, but that's about what it looks like. This is a classic curve to use implicit differentiation on in Calc 1. Now what I want you to do is to try to use this theorem that we just had, that the implicit function theorem for 2D, okay? So think about how you would start. Say out loud what you're going to do first, and then try it out on your own. Use the implicit function theorem. Okay, here we go. So the implicit function theorem said that I need the partial with respect to x. Well, first I need to move everything over and get an actual function, right? So here's what I'll do first. I'll call my function x cubed plus y cubed minus 6xy, set that equal to 0, right? So this is my function. I need to compute the partial with respect to x, the partial with respect to y, put them one over the other, and make it the opposite. So here we go. Oops. Partial with respect to x, partial with respect to y. There's the opposite. Simplify, and you get this. Done. Instant. Yeah, so now I say this. So for those of you that remember, or if you don't, compare this to the process that you did back in Calc 1, or compare it to the implicit differentiation process we did, oh man, I think in the last section, 14.4. 14.4? Yeah, 14.4. But you can do it that way, right? Remember, you basically differentiate both sides, right? And then you would solve for dy dx. Well, now this gives you a shorter way of doing that. Just compute the partials, divide one by the other, and then take the opposite. So it's much quicker, much quicker. Naturally, you can extend this to higher dimensions, so we'll just stop at 3 for this one. This is the implicit function theorem for a function of 3 variables. So everything goes up a dimension. Say your function is defined on a ball, right? So like a ball, a solid ball containing the point ABC, and ABC is a 0 of that function. The derivative with respect to z cannot be 0. We need all of these to be continuous inside the ball. Then this equation will define z as a function of x and y near this point, and the function is differentiable, and here are the partials. Partial z, partial x, partial z, partial y. Very cool stuff. Very cool stuff. It's not so bad, right? That one's actually not so bad. That's the implicit function theorem. All right, on that note, let's play. So I'm glad that this one is not as long. Hopefully it wasn't too bad. Use the diagrams. Like, I swear, if you draw the diagrams, it's a lot easier to figure out what you're supposed to differentiate and like what you're supposed to multiply and add up, all right? Okay, on that note, I'll say bye. Thank you again for watching, and I will see you next time.